Hello everyone, it's Benny, and welcome back to the 3D game programming tutorial series. Last time, we managed to get our interaction system to actually do something. If our monkey head touches a cube, we're interacting! Hey, isn't that cool? It is cool, but it'd be nice if we could make it do something actually useful. Now we know the interaction system does what we intended it to do, so let's make it do something interesting. That is the topic of this video. We're going to be doing basic collision. Basically make the monkey head so it can hit the cube and then, well, not move. The cube acts like a solid object. Let's do it. So, the first thing we need to do is set up our test interaction so it has the appropriate components. And we're going to do something somewhat basic here first, but it will lead into what we want to do. So that's what we're going to do. So we're going to add interactor component type. Needs a transform component ID. And we also want the collider component ID. And same thing for interactD. We want the interactD to have a transform and collider. This shouldn't change anything because everything has to have a transform and collider to be interacting to begin with. But this way, now we have access to these components in our interact method. So, what are we going to do? Right now, I just want to make these objects respond to the interaction. That's my first goal. So, to get some response, what I want to get a transform reference. I'll call it transform. And this is going to be the interactor's transform. So I'm going to look at interactor components, index 0, because the transform is the first component in the interactor. I'm going to cast this to a transform component pointer. And once I have all this, I'm just going to say arrow transform. So this should be pretty familiar. This is basically what we do with ECS systems. And now we have a transform. So what do we want to do with the transform? I'm going to keep this pretty simple. I'm going to make it so that when the objects are interacting, they spin. Very simple. So I'm going to say transform.setRotation to transform getRotation. And we need actually a rotation to rotate this by, so I'm going to create a quaternion. It's going to rotate around the axis. Let's spin around the z-axis. I think that'll be fun. By just delta. Don't really care about the rotation speed. So it's going to rotate around the z-axis by delta. I'm going to take our rotation. Oh, I actually want to name this something. Or do I? I could just sort of inline here, so why not? So multiplied by this quaternion. There you go. And one last thing you want to be careful of is once you apply a rotation like this, you're going to want to normalize it. So there. And with all this, this should give us basically things spinning when they interact. So let's go ahead and let's test this out. And we spin a little bit. They stop spinning at some point, but they do spin a little bit. Which might leave you wondering, hey Benny, why do they stop spinning? You might be tempted to assume this is something with our interaction system, but it's not. This is actually a subtle bug in the math code that I have been unable to solve for a while now. And I'll go ahead and show you what it is. So in math to aabb.cpp, we have the transform method. And what this method does, very straightforward, well, maybe not that straightforward, but it transforms the center point to its new location. That should make sense. The center is independent. And also does a little bit of interesting math. It transforms the extents of the AABB by the absolute value of the matrix, which math says should give the extents the correct absolute value of the final rotated AABB, so you should just be able to add and subtract to get the new min and max. For some reason, that's not working here. I'm not entirely sure why. I'm sure I'm just overlooking something in this code, but it doesn't work. Mathematically, it should work, but it doesn't. So to solve this, we're going to fall back to the naive way of doing AABB transforms, which is generate a point for every corner of the AABB, transform every one of those 8 points, and get the minimum from those points and the maximum from those points to get the new AABB. It's a very brute force way to do it, but you know what? It works. If I build and run now, all of a sudden, hey, rotation works as expected. But that's actually kind of cool, because what you can do is you can, align your monkey head like this. And because AAVBs are, they aren't a perfect fit for the object shape, it'll sort of rotate until it reaches a point where they actually, like this, where they aren't intersecting anymore. So that's kind of a fun thing to do, just align like this and boop. But yeah, so we can indeed affect the transform of objects with our new, our new system, our interaction system. With that out of the way, let's move on to the next part of the problem. Because we don't want to end with just everything rotating. What we want is for moving objects, if they hit each other, to change their motion somehow, whether it be stopping, bouncing off, just some way to change their motion, respond as if they've hit each other. So we're going to want to add more component types to this. Specifically, we want the motion component for the interactor and a motion component for the interactee. Technically speaking, we could get away without a motion component here, but for now, we're just going to handle the case where both objects are in motion. We're not going to worry about hitting solid objects. We're going to say everything must be in motion for this to work. And this is going to cause a problem, as you'll see very shortly. Because if I build and run right now, as you might predict, this doesn't do anything. All of a sudden, our interaction is no longer happening. And there's a very good reason for this. The reason is our player entity, the one we create right here, you might notice, does not have a motion component. Yeah, they just sort of stationary, does nothing. And also, this component also does not have a motion component. But for now, I don't want the motion component to actually do anything, so I'm just going to have everything stationary. We're going to go ahead and add a motion component to both of these. And this should work, technically, but it's still going to be a bit of a problem, mainly because our player's movement component doesn't work with the motion component. So even if we change the player's motion component to respond to the collision, it's not going to work because the player's controls sort of override, they ignore the motion component. So our next thing we're going to do right after this immediately is we're going to go to our game components and systems, we're going to go to our movement control, and we're going to change our movement control system. Now we should have a motion.hpp right here, and this shouldn't depend on our movement system, which is good. I want to double check that to be sure, but it doesn't. Good. Because we're going to include motion.hpp right here. So include motion.hpp. And we're going to add a component type, a motion component ID. And there we go. We're just going to add in here, instead of just movement control component, motion component called motion component. And it's going to be a type motion component. And it's going to be components index 2. There we go. At this point, we're going to take a slight detour. Right now, our motion system is very simple. Like, even ignoring the fact that we're ignoring the motion component, what we do for movement is very simple. It's if we have the up button pressed, we move in the up direction at a specific speed immediately, no acceleration, and continue moving at that speed until up is released, at which point we move at 0 immediately, no acceleration. That's not very realistic to how motion works. Wouldn't it be more interesting if we had an actual acceleration curve? We press up, and there's some acceleration until we hit the maximum speed. And that maximum speed isn't just some arbitrary value, it's determined by how much resistance there is to motion. So, yeah, there's just a little bit more going into it. And it's not going to be a huge change, don't worry. It's just something we might as well do while we're here, because we're about to have the critical component to make that sort of system possible. So, the critical change we need to make is we're going to get rid of the transform and this new position. We're just going to get rid of all this logic. And what we ultimately want to do is something like motion component dot velocity, and we want to set that to what we had before, just we aren't performing the integration here. We're letting the motion component, or like the motion system, perform the integration. And it will combine that with all the other relevant motions and forces applying to the player, so this doesn't have sole dominion over how our player is moving. We can have the player get blasted by something, and the player can only have so much power to fight against it. And that's kind of cool. But, yeah, so this right here is the major thing we're doing. We're saying movement times input amount. And you immediately notice a problem with this because we're assigning the velocity to this. This can't take into account any other forces. So really what we want to do is we want to change the existing velocity based on how much the input has changed. And we don't really have a good way of doing that yet. So this is where the big change comes in. Well, I say big, it's not really much of a change, but we're going to change the way our motion controls is implemented. Right now it's a pair of vector 3F and input control pointers. And that's great, but we also want to know what the last value of this input amount is. So we can get sort of a delta. We can determine how much this input has changed, and then from that we can determine how much we need to update the motion component's velocity to reflect how much the input has changed. So the change that makes this possible, really simple. We're going to create a new struct called movement control, and this is just going to have basically what we already have in this SD pair. We're just changing it to a structure, which might lead to the question, hey Benny, why are we changing this to a struct all of a sudden? You'll see in just a second. So our input control I'll just call input control. Our vector 3F I'll call movement, sure. And we're going to create a constructor for this. So I'm going to create a constructor, movement control, takes in a vector 3F reference, movement, and an input control pointer, input control. There we go. Simple as that. Though actually, right, I need to actually assign them. Don't forget to assign your constructed variables. That's kind of important. But yeah, just movement becomes movement in, and input control becomes input control in. And I need to change these names to in so they do not conflict with our variable names. And this should be everything we need in our struct. Well, almost. So right now this is just sort of a drop-in replacement for the function the pair is providing us, except with a custom struct. So there you go. It's now an array of movement controls. Hey! So what? Here's why it matters. What I want to do here is I want to add a new float that I'm going to call last input amount. And this in the constructor is going to be assigned to 0. Oh, really, I could be a little bit more intelligent about this and assign this to input control in get amount. So there you go. So we start off our movement control with knowledge of what the last input amount was. And this also makes this logic right here a little bit easier, because now we can say movement controls sub I, we can say dot movement, and this can be dot input control. Though, yeah, the name works. It works. So with all this done, now what I can do is I can say float input delta, and this is going to be input get amount, and I can subtract, you guessed it, I'm going to take movement controls dot last input amount, and there you go, this is the input delta. So now I can say velocity plus equals movement times input delta. If the input hasn't changed, this will do absolutely nothing to the velocity. If it has changed, this will update the velocity to reflect the change. So that's actually really nice. But as I said, since we're here, we're going to do something a little bit fancier than just changing the velocity directly. Alright, so everyone, I want you to brace yourselves. We're about to get into some real fanciness here. And you might not be ready to handle the fanciness, but just go along with me, alright? It's going to be alright. What we're going to do here is we're going to delete velocity and replace it with acceleration. There we go. That's our new movement system. Simple as that. There's only one more thing I want to do beyond this, though. And that's just because if we do it like this, we could accelerate to infinite speed. So just to put a little bit of a limiter on the speed, I'm going to say motion component dot velocity, and I'm going to say times equals 0.95. Does that even work? I don't know if I actually implemented times equals, so I'll just say equals that times 0.95. There. And this is just going to be a way to, well, reduce our velocity a little bit every frame. Now you might notice this isn't using the delta, so this technically isn't accurate, but honestly this constant shouldn't be here anyway, so I'll just go ahead and leave a comment saying, to do, this is a cheap hack to get resistance for now. Replace with a proper system later. So there we go, we have a cheap hack to have some form of resistance to our motion. So we can't accelerate infinitely, we can only accelerate up to a very particular maximum speed. So to finish this up, I'm just going to change our movement controls last input amount to input amount. So there you go. In fact, I don't even need to refer to this directly, I just need float input amount. So I'm actually going to say that. I'm going to say this equals this arrow get amount. And just replace it here. Does it really make a difference? Probably not, but I feel like it, alright? We just need the input amount. I'm just going to use the input amount. There you go. And now what we should be able to do is we should be able to go to our game.cpp. Gonna go ahead and move you over. And we're going to just change our initialization of our movement control component to, yeah, right now we're using std make pair of all this. This should be as simple as replacing this with movement control of this. It should be as simple as that. And with that, we should be done. And it is time to deal with the oversights, because I made quite a few this time. So first of all, motion component. That's a pointer, not a reference. So where it says motion component acceleration, that should be an arrow. Same thing with motion component velocity, should be an arrow in both those places. Next up is at movement control at the top. See where I have, I'll scroll up for you, see where I have this constructor defined, movement control, : movement control? Yeah, you don't need that when defining the constructor inside the struct itself. I don't know why I thought that. I guess just brain freeze, it happens. So, but yeah, whoops, wrong button. But yeah, you don't need that. You can just get rid of that and just say straight up movement control. Finally, because everything's between the movement control component and motion component now, we don't need the transform component. We can just get rid of that. So we're going to get rid of that dependency. We're not going to add the component type transform component, nor are we going to get a transform component in update components, and we just need to change those indices to 0 and 1. And with that, that should be everything I missed. And now we should be able to build and run and have a brand new acceleration-based movement system. So if I press the up key, look at that, we accelerate slowly and whoa! Yeah, I can accelerate over it and rotate. I can keep accelerating in direction. If I release the key, you notice there's a little bit of like slowdown delay. There's a little bit of momentum to it, which is kind of cool. Now, obviously, it's sort of hackish right now, so I wouldn't go too far parameterizing it, because it's unlikely they'll generalize when we have a more proper system in place. But I would like it a little faster, so where I have movement controls, I'm going to change this to 30. So we are accelerating a bit more. There we go. Just a little bit more starting speed should be fine. And I'll just leave it like that. This is a fair enough movement system. And yeah, so now we have, well, this brand new movement system. But we're still not doing anything interesting when we touch, well, this cube. How can we handle that? Well, I don't have enough time left in the video to implement a proper collision response system, So instead, let's do it the hackish way. What I'm going to do is I'm going to duplicate this line. We're going to create the transform. And we're just going to change this straight up motion component. So interactor component sub 2, that is the motion component. And I'm going to change the name to motion component. And I'm also going to make this a pointer. At this point, we no longer need the rotation. And we're going to do the very hackish way of implementing collision. What I'm going to do, say, take the velocity, and I'm going to set that to the same velocity times -1.1. So we're actually going to gain a little bit of speed from the collision, which is technically aphysical, but there's good reason for this. So what I can do now is I can accelerate into it and boing. So I can bounce off of it. I can just accelerate into the cube and I just bounce right off. So there we go. Now we have some form of collision and it's working. I can keep bouncing into it and nothing happens. And this is why I have that little extra bit there. Because yeah, this is aphysical, but I'm also not actually solving the collision. I'm relying on this velocity boost to move the monkey head far enough away from the collision site to actually solve the collision. So there's sort of like a fudge factor to make it probably likely that this collision will be resolved after the next time step. So yeah, and it's not right, but we are having our AABBs collide. And there's a lot to be desired here. Like I said, this is a very hackish way of doing it. This is not correct collision response. Like, what if you don't want to bounce? What if I just want the monkey to hit it and that be that? For that, you actually will need a proper collision solution to do. And also there's the issue of, we're only colliding the AABBs. What if I want them to actually collide with the actual mesh? But, as you see, our interaction system does support some form of collision now. We are on the right track. And this is incidentally about where I wanted to be before we do, yeah, our first game project. So we're going to put proper collision on hold. Probably. I may decide to come back to it, but I think I'm probably just going to let it be. And we're going to move on to our first proper game. And that should be starting in the next video if I don't go back to collision response for some reason. So thank you very much. I hope you're hyped for this. This is another really big phase of the series. And yeah, we're going to be starting to make an actual game out of this. Well, it'll turn out like, find out next time. I hope you enjoyed. I hope you... Don't forget, there's a Benny Discord, and you can get early access to the next videos by becoming a patron on Patreon. Thank you very much to all my Patreon supporters, and especially those listed in the video description, for making these videos possible. Thank you very much, and I will see you all in the next video.